So second part of the video for IMFAs is we're starting off talking about covalent network solids. You don't see it in liquids, you just see it in solids. Let's take a look at some of the properties and what's going on. So in a covalent network solid, basically it is a lot of strong covalent bonds holding many atoms together. And typically what you wind up with is one big particle. They talk about it being one large molecule. They're true covalent bonds. So sharing of electrons, there's not a whole lot of elements that will do this, but we'll go through what they are. So you've got, again, true covalent bonds, and the end of there's not really any molecular formula. It's carbon or it's silicon, because the end of the molecule is wherever the atoms stop. So what this winds up doing is it creates a substance with such strong IMFAs or such strong bonds that they're very hard, they're very strong, they have very high melting points. Usually they're non-conductive. The one exception is graphite, and we'll take a look at that in a minute. So some examples of the elements that are going to form a covalent network. Carbon, we'll do it in two ways. You can get two allotropes. So allotropes are just two network solids like isomers are to molecules. So different arrangements of the atoms within this big conglomerate. So a diamond is one way of arranging carbon atoms. Graphite, which is what your pencil is made out of, not the wood part, but the writing part, the black stuff. It's not lead, it's actually graphite. Has a different arrangements. Silicon, germanium, silicon dioxide. This is the only molecule that covalent networks. And then there are other synthetic combinations. As long as you have about 4 electrons per atom, you'll wind up with that. So I know in first year we talked about boron will do it as well. So you have carbon, silicon, germanium, boron, and silicon dioxide. Typically those are the 5 we credit for giving us covalent network bonds. And again, you can have combinations of those. So here is an example of diamond. You can see on the left as well as in the center slide, you've got diamonds where you have a tetrahedral organization with every atom. So you have one carbon bonded to 4 others, which are bonded to 4 others. So you get this 3-dimensional hexagonal network. That's very strong. On the other hand, graphite, carbon actually doesn't have 4 bonds, it only has 3 bonds. So that one extra electron that's not involved in covalent bonding is actually the reason why graphite will conduct electricity, because it will flow from atom to atom to atom, just like what happens inside a metal. So notice in graphite you have these 2-dimensional planes, and then these are just London forces holding the atoms in one layer close to the atoms of another layer. So when you write with a piece of graphite, when you push that pencil down on the paper, what you're doing is you're sloughing off one of these layers and letting it stick to the paper. And then in the pencil tip, the rest of it goes. So here's another example. You have silicon dioxide, and so notice SiO2, they just kind of keep going. There's no differentiation between, so sulfur bonded to an oxygen, bonded to another sulfur, bonded to an oxygen, bonded to another sulfur. So you don't really have individual SiO2 atoms. So this is more like a empirical formula, like a formula unit, like it was ionic, as opposed to it being the actual molecule. And you can see that there's crystalline SiO2 and then amorphous SiO2. This is where glass comes in, silicon dioxide, and glass is amorphous. So it has just this random patterns. And then something new in terms of covalent bonding, you get these fullerenes, which are rings of carbons, three-dimensional rings. These are called buckyballs. They are starting to find very useful pieces of information about them and for them. So those are something to look for in terms of materials of the future. All right, then we're going to move on to, so we've talked about metallic things, we talked about ionic things, we talked about the special case of these covalent networks. Now let's get into the kinds of IMFAs that molecular substances have. So London dispersion forces, if you remember, are the weakest. They are the types of forces that occur between nonpolar substances or noble gases. And so the idea here is that, remember, in nonpolar substances, you don't have a distinct plus or minus pole, or in the noble gases, you don't have a distinct plus or minus side. They're nonpolar, so the electron density is evenly distributed. So what happens in order to get the molecules to attract each other, since there's not pluses and minuses? They form what we call temporary dipoles. And how does that happen? Well, the electrons are going to be slightly distorted by neighboring molecules. So remember that electrons are constantly moving. So as electrons move, they can influence the electrons of other atoms. So basically what's going to happen is as the electrons move, you get kind of a sloshing idea. All the electrons move in one direction, and then they'll move back in the other direction, kind of like what you see happening to water. And so as a result, you get temporary dipoles created. So here's an example. You've got helium attracting the two electrons here because they just happen to both be on the side closest to the nucleus. And so all of a sudden, you have more electron density on the left side of the molecule, less electron density on the right side of the molecule, now, or atom in this case, and now you have polarized the structure. And once you polarize one, it can influence adjacent atoms around it. So you can get a whole lot of polarization happening. This is a pretty cool slide here. Got to thank Mr. Hinton, who's the former AP Chem teacher at Deerfield, for making this one. So nonpolar molecules, initially electron density pretty evenly placed. But if I get a temporary dipole to happen between these two, so the electrons have shifted one way or the other, what's going to happen, it's going to influence its neighbors. And then they will in turn influence everything else. And pretty soon you have everything kind of polarized. And again, these are temporary, so they're going to shift back. Okay, and what happens? You get shifting, and notice that now we have the shift of electrons back the other way, and so you have this kind of sloshing going on, where the negative side is over here, and then the negative side is over here. Dipole-dipole attractions are what happens between polar molecules. So you've got permanent dipoles, so really what you're doing is it's like little magnets being attracted to each other. You have the plus end of one molecule being attracted to the negative end of the other. So you get a much stronger attraction than those temporary polarizations in London forces. So polar molecules, under the same conditions, a polar molecule is going to be a liquid, whereas a nonpolar molecule might be a gas. Or polar molecule will be a solid, where a nonpolar molecule would only be a liquid. So here's an example. Again, I've got those polar atoms or polar molecules, chlorine slightly negative, hydrogen slightly positive. They're going to set up so that their ends are arranged in order to attract the other kind. So you wind up with attractions between all these different polar opposite ends. So those are dipole-dipole attractions, and these are permanent. These aren't going away, whereas the London forces will disappear. Then you have hydrogen bonding, which is ultra-strong dipole-dipole attractions. Again, it only happens between atoms of fluorine, oxygen, and nitrogen that are bonded to hydrogen. So the reason is all three of these are relatively small atoms. They all have relatively large electronegativities, and so they are able to pull that little itty-bitty hydrogen well into it. Well, not the hydrogen itself, but the electron from hydrogen, going to be pulled really tightly against these three atoms, which means it's very polarized. H is very plus. It's not +1, but it's very positively charged. Molecules containing these kinds of bonds have much higher melting and boiling points than otherwise would be expected. And for us, the geological and biological systems of the Earth would be very different if hydrogen bonding didn't exist, because water molecules hydrogen bond. So here's just another visual. Water is a liquid at room temperature. It doesn't boil until, it doesn't form a gas until it hits 100 degrees. But if you look at all of these other molecules, some of them much heavier than water, they are all gases at room temperature. So water stays a liquid at room temperature, while all of these very much heavier molecules become liquids, or gases rather, because of the hydrogen bonding. So again, you can see hydrogen bonding. It doesn't have to be between two of the same atoms. It could be between two different ones, but it's got to be the nitrogen, oxygen, or hydrogen of one molecule with a hydrogen of another molecule in the same situation. And that's how we get ice crystals. Remember that these are hydrogen bonds. These are between molecules, not within molecules. So that's one important thing that you want to remember. These within the H2O, those are the covalent bonds. But the green ones are the hydrogen bonding. These are not hydrogen bonds. These are just covalent bonds. Hydrogen bonding is between molecules. Okay, so much shorter distance here than between two molecules. All right, so that gives you a quick background. I think your book does a nice job of summarizing properties. We'll also review that and hit the highlights in class as well. So please do read the text, read the sections that you are assigned, and we'll talk about everything in class.